All right, now that we talked about the integral test, I want to use that essentially to give us another test for a particular type of series that we call P series. So if you remember from our improper integrals, we looked at integrals, improper integrals of this form, right? Infinite limits of integration going from 1 to infinity, 1 over x to the p. And we saw that that integral, remember, had a value of 1 divided by p minus 1 if the value of p is greater than 1. Otherwise, then the integral actually diverges. And so if p is less than or equal to 1. And so that can be used with the integral test to immediately say something about this series, right? This infinite series of this form. All right? That this series, therefore, is going to converge if p is greater than 1 because the corresponding improper integral converges, essentially, right? Converges because it has an actual value. And it diverges if p is less than or equal to 1. Keep in mind that the again, if any P series converges, the sum of that series is not immediately known, is not equal to the value of the improper integral. And we talked a little bit about that in the last video. So this is a real quick and easy test, right? Here's an example of a series, 1 divided by n squared, and when n is 1, we get 1. When n is 2, we get 1/4. And n is 3, we get 1/9, 1/16, and so on. Well, this is a P series, right, with P equal to what? 2. And since that indeed is greater than 1, right, what do we know? That this series converges, or is convergent. And it's just as easy as that. What about this one down here? Is this a P series? Yeah, remember the square root of n is the same as n to the 1/2 power, and so this is a P series with p equal to 1/2. Well, 1/2 is less than or equal to 1, and remember P series, if the value of p is less than or equal to 1, are going to be divergent. And that series diverges. Now, the one series we looked at and proved with the integral test was divergent, is also a P series, namely the harmonic series. All right, the harmonic series itself, notice, is a P series with p equal to 1. And of course it diverges when p is less than or equal to 1. But that's kind of the boundary case, if you will. So if p is equal to 1 or anything less than 1, then the P series is going to be divergent. Excuse me. But if p is greater than 1, then that series is going to be convergent. So the harmonic series is kind of the borderline between those cases. Now, with this, now I want to look at one last thing in this section, and that is comparison tests. And what we're going to do is, given a series that it's going to look very close to perhaps a P series or a geometric series, one that we can quickly, the P series and geometric series, we can quickly determine their convergence or divergence. And if we can compare the given series to one of these, then we might be able to say something about that given series. And just remind you of these two particular ones then, the geometric series we looked at previously, right? They're infinite series of this form, where r is that fixed value we're multiplying by to get each term, right? So and when n is 0, I get a. When n is 1, I get a times r. When n is 2, I get a times r squared, and so on. I just keep multiplying by r. Adding all those terms up, that series is going to be convergent if what? The absolute value of r is less than 1. In other words, if it's strictly between -1 and 1. Otherwise, if the value of r in absolute value is greater than or equal to 1, either greater than or equal to 1 or less than or equal to -1, then that series is divergent. So we can quickly determine that. And then for P series, we know what we just said, they're convergent if what? P is greater than 1, and divergent if P is less than or equal to 1. So let's take a look at first of all, the direct comparison test. So suppose we have two series. Again, we're dealing with terms that are series with positive terms, okay, greater than 0. And then we also have the terms of the series a sub n are always less than or equal to the terms of the b sub n for all n greater than or equal to 1, or any other positive integer. And then we have these things. And I want to draw a little picture just to illustrate, why these two statements are true. Okay, so let's suppose the a sub n's are always less than or equal to b sub n. So I'll do the a sub n's in green. So here's a sub 1, right? And I could think of, right, so this height, right, this is a sub 1. That's the output. When I plug in 1, the output's a sub 1. But I can think of this geometrically, if I think about, again, we've done this before, this rectangle right here. What's the area of this rectangle? It's a sub 1, right? The area of this rectangle. And then let's suppose a sub 2 is right here, right? Then I can also say what the area of this is a sub 2, right? The area of this rectangle. And so on. So maybe here's a sub 3, a sub 4, a sub 5, and so on. The b sub n's, as we said, are greater than or equal to the a sub n's, are bigger. So maybe b sub 1 is up here, right? So that this is the height b sub 1, so plug in 1, output b sub 1. But again, I'm going to think about this geometrically as this rectangle has width 1, height b sub 1. So this is b sub 1, which is this, plus, right, everything, the green area all the way up, right, all of this. And then maybe b sub 2 is here. And then, we've got this rectangle representing b sub 2 is the same as the value b sub 2, because the width is what goes all the way down here. And so on, right? So maybe here's b sub 3, b sub 4, b sub 5, right? So the b sub n's are greater than or equal to a sub n's, or the a sub n's are less than or equal to b sub n. So if we've got that, let's come over here and see. If the b sub n is convergent, what would that mean? That would mean the area of all of these blue rectangles all the way to infinity, if we add them up, they must be finite, right? If the infinite series is convergent and has a sum, right, that is finite, okay? But what's that mean? Since these green boxes, right, are all less than, right, clearly the sum of all the blue boxes, and the blue boxes add up to a finite amount, the green boxes have to add up to a finite amount. Therefore, the series a sub n is convergent. You see how that works? If a sub n is divergent, what's that mean? Then all the green boxes, if I add up all these green boxes, then that is not a finite quantity, it's infinite. So in other words, as I keep adding these areas together, it just keeps getting larger and larger, it does not approach any finite value. And so we say that it's an infinite series that diverges to infinity. Well, if the green boxes all are an infinite area, the blue boxes are more than the green boxes, and so therefore b sub n also is divergent. See how that works? Now we got to be careful. What if I said the a sub n is convergent? What if that's what I knew? What if I knew the green boxes added up to a finite quantity? Does that tell me anything about the b sub n's series? About the blue boxes? No, it doesn't. The blue boxes could be convergent, they could be divergent. So if the series a sub n is convergent, that tells me nothing about the b sub n's. So the direction of this inequality matters. The direction of this inequality matters. Now, what do we do with direct comparison? As I said, we compare with often geometric series or P series, ones that we can quickly determine. And I want to look at this example here, first of all. All right, this one here looks kind of like a P series, right? We did one where it was, 1 over, the square root of n, right, which is n to the 1/2, so that's p equal 1, p equal 1/2, but we've got this extra 3 to the n in the denominator. But let's see if we can compare those two. There's the terms of our series here, and let's compare with this series, right, which is the same as 1 over n to the 1/2, right? So this comes from a series, right? This comes from a series that is a P series. P is equal to 1/2, which is again what? Less than or equal to 1. and that means the series, right, 1 over the square root of n diverges. Right? It's a P series that's divergent. Now, what's the inequality, though, between these for values of n what equal 1 to infinity, right? So when n equals 1, n equals 2. Well, clearly, both fractions have the same square root of n in the denominator, but this one has an additional 3 to the n. For any value of n, then what do we know about this denominator compared to this denominator? It's always bigger, isn't it? Right? When n is 1, it's, what, 3 to the first power? It's 3 times as big as that one. When n is 2, it's 3 squared, 9 times as big as that. When n is 3, 3 cubed, 27. It's 27 times the square root of n. 27 times as big as this. So for any value of n greater than or equal to 1, this denominator is bigger than this denominator. But if this denominator in this fraction is bigger than this denominator, what do we know about these two fractions? Well, the bigger denominator, overall, this fraction is what? Going to be smaller, right? 1 divided by a bigger number is smaller than 1 divided by a smaller number. And so the direction of this inequality, right, this is smaller, right? Less than or equal to that. And so does this inequality help, as we were talking up here? Does that inequality help? And the answer is no, right? Because this series diverges, what do we need? If A sub n is divergent, we need, in order to say B sub n is divergent, what do we know? The B sub n's have to be greater than or equal to the A sub n's, right? But ours are what? Less than or equal to this. So this thing's diverging, our terms are less than or equal to that, we don't know. So this does not help. So this whole thing we went through was a waste of time, in a sense. Not really. We did learn something, just it's not useful, right? It does not help, right? Can't use direct comparison, right? Because the inequality is incorrect. However, we could have also compared what our terms with this, right? Which is the same as 1/3 to the n. Well, terms, the 1/3 to the n, what are those terms? 1/3 to the first is 1/3, 1/3 squared is 1/9, 1/3 cubed is 1/27. That's what? That's a geometric series with the value of r equal to 1/3. So if I'm looking at this series, right, 1/3 to the n, this is convergent. Since the value of r, right, is less than 1 in absolute value, r is equal to 1/3, right? So this is convergent. Now, compare these two fractions. Again, notice the denominator here is always going to be bigger than the denominator here, because here we've got an additional factor of the square root of n. So when n is, well, was n is 1, I guess they're equal, right? When n is 1, square root of 1, I get 3 and 3. But when n is 2, I get, something a little bit bigger. Or when n is 4, for instance, I get square root of 4 is 2, I get 2 times that. So this is bigger, so this fraction then is smaller than this one by the same argument we had there. And so the inequality is this way. Does this help? Yeah. Since this series is convergent, right, the B sub n's, and the terms of the series we're looking at, right, the A sub n's, are less than or equal to, right, these terms, then our series also is convergent. So this now allows me to say what? By direct comparison, with that series, the series 1 over square root of n, 3 to the n, is convergent, or converges. Now, I'm not able to determine a sum for this series, but I am able to determine whether or not it is convergent or not. Okay, so by direct comparison, so we compare it to a series, we know whether it converges. We know it converges, and all our terms are less than or equal to that, so it's also going to converge. Take a look at this one here. Okay. What would we compare 1 over the natural log of n to? What can we compare it to? I'm going to compare it to 1 over n. And we know something about this series, but why would I want to choose that? Well, first of all, think about the graphs of these two functions. Right? for the function n, if you will, right? Plug in 1, output 1, right? So the function n will just look like this, right? So 1, 1, 2, 2, 3, 3, 4, 4, right? It's just the line y equal n, or y equal x, if you want to think about it in terms of a function, right? And what about the natural log function? Well, remember the natural log function, right? At 1, the natural log is 0. And as we approach, of course, as we approach 0, we've got this vertical asymptote going down here, but this way we're going to infinity as well, but at a slower rate, right? Slower rate. So natural log of 2 is less than 2. The natural log of 3 is less than 3. The natural log of 4 is less than 4. So you see, notice our series, we're starting at 2, of course, because the natural log of 1 is 0. We've got a problem there. So we're starting at 2, right? And so for values of n 2 or greater, we can clearly see that n is bigger than natural log of n. So if n is bigger than natural log of n, then this fraction is smaller than that one. Right? This fraction on the right is smaller than this one. Or saying it another way, this fraction on the left is what? Bigger than this one. It's bigger than this one for n greater than or equal to 2, right? So for n greater than or equal to 2. And what do we know about the series? That's what? That series, that is the harmonic series, right? Or a P series with P equal to 1. So this is divergent harmonic series. It's a P series. P equal 1, right? P equal 1. And either way, it's divergent. But all our terms are greater than or equal. So the A sub n is divergent, and you have another series whose terms are always greater than or equal to these terms, and that series is also divergent. So this series, its terms, all right, this series is divergent. The terms of our series here always greater than these, and therefore our series diverges rather by direct comparison. And again, we're quoting which test we're using. Okay. Now, direct comparison is nice. Of course, you've got to get the inequality in the correct direction, right, in order for this to work. And that becomes problematic in an example like this. What might I compare this series terms to? Okay. Well, as n goes from 2 to infinity, as n gets larger and larger, the bottom polynomial, if you will, this polynomial in the variable n, in the index n, it gets dominated by the end of the fourth term. I mean, for large values of n, like n equal 1,000, a million, a billion, then basically it's just n to the fourth. And then I can simplify. What's this fraction simplify down to? N squared divided by n to the fourth. Simplifies down to 1 over n squared. And this comes from what? This comes from a P series, if we think about it, right? 1 over n squared. Right, it's a P series with P equal to 2, which is greater than 1, and so it is convergent. All right, it's convergent. However, when we compare, right, n squared over n to the fourth to n squared over n to the fourth minus n minus 1. Think about these two denominators now. N to the fourth here. N to the fourth minus n minus 1. Since I'm taking away n, and then I'm taking away 1, by the way, for n equal 2, 3, 4, 5, then this denominator is always smaller than this, right? N to the fourth, and then I'm taking stuff away from n to the fourth. So this denominator is smaller. Both have n squared up top, so that's the same. But if this denominator is smaller than this, the smaller denominator means the overall fraction is going to be what? Bigger, right? Greater than or equal to, right? And do you see the problem? that's not going to work for us because this series is convergent. In order to say that this series is convergent, we need to have the terms less than or equal to it, right? So if this series here converges, then the terms of our series, if they were less than or equal to the terms of this series, our series would be convergent. But that's not the case, okay? It turns out that this series is convergent, but the direct comparison does not work. Direct comparison does not work. So, do we have an alternative? Yeah, there is. There's one more test I want to show you that's kind of interesting. I'm not going to prove it to you, but it is known as limit comparison. Okay, limit comparison. And here you're comparing, again, two series with positive terms, and we want to look at, this case, the limit as n goes to infinity of the ratio of the two terms. Okay? If that limit is approaching some real number c, right, where c is greater than 0, then either both series converge or both diverge. Okay? And what this is saying, essentially that is, if as n is going to infinity, then a sub n over b sub n is about equal to c, is what we're saying. The limit's getting closer and closer to c, right? Oops, that's a b sub n, sorry. That ratio is getting closer. So a sub n is just a scalar multiple of b sub n, right? And so when we're looking at the corresponding series, right? Sorry, I'm just making all kinds of mistakes. That's a c. c times b sub n. Then I'm looking at these two series, right, if that's the case for large values of n, essentially, and you kind of get the feeling then if this series is convergent, then this one does too, because the c is just constant multiple can come out, right? And so, they kind of go hand in hand if a sub n is equal to c times b sub n, right? So, and on the other hand, if a sub n's, this series diverges, right? And since a sub n is about the same as this is a sub n about, right? Then this series is also going to diverge, right? I'll just say approximately equal these two series are. So that's what we say, that either both series will converge or both will diverge. And there I don't need to do any comparing between these two series. So let's go back to our previous example. Remember, we were going to compare to what? We were going to compare to 1 over n squared, if you remember, right? Again, I got that by just taking the highest degree term up top, n squared, highest degree term on the bottom, n to the fourth, and simplifying it, right? N squared divided by n to the fourth is 1 over n squared. So that's a common way of doing that. And so this is a convergent P series, we've already said, right? Because P is equal to 2. But then let's take a look. What's the limit as n goes to infinity of the a sub n's? We'll let this be the a sub n's here. All divided by the b sub n's. Okay. Well, let's clean this up before we push the limit through. A fraction divided by a fraction is what? We take this fraction up top, and we divide by 1 over n squared, same as what? Multiplying by the reciprocal. Okay, so I can now multiply up top, and what do I get? N squared times n squared is n to the fourth. In the bottom I get n to the fourth minus n minus 1. And this looks familiar, right? We've looked at limits at infinity before. Notice I can multiply both the numerator and the denominator by the highest degree term in the denominator, in this case. And I get 1 up top. Down below I get 1 minus what? N divided by n to the fourth is 1 over n cubed. 1 divided by n to the fourth. Okay, so this is one technique I can use, and you'll notice that the denominator, so I'm multiplying by 1, right? But down here, this is going to 0, and this is going to 0 as n goes to infinity. And this limit therefore equals 1, which is indeed greater than 0. Okay. Another way, by the way, notice the form of this limit. Form of this limit is infinity over infinity, so you could also use L'Hopital's rule on it and get the same thing. So the limit is, you might have to use L'Hopital's rule a few times, but the limit is 1, and that's important, right? Because notice this limit C has to be positive. Has to be positive. And if it is, then both the series converge or both diverge. But since this one converges, and this limit C is greater than 1, then our series also converges. So I can say by limit comparison, the series n squared over n to the 4th minus n minus 1 also converges. So limit comparison is kind of nice. You can compare to a series that you know converges or diverges, and you don't have to do that inequality thing we were doing with direct comparison. But now this limit, right, of the ratio of the terms of the two series, right, that has to be a limit you can find, and it has to be a finite, it has to be a real number, can't be infinity. It has to be a finite number that is positive. Okay. Let me do one more example with limit comparison. Kind of a fun little series here. All right. Now as n goes to infinity, 1 over n we know is going to 0, and sine of 0 is 0. So the terms of this series are indeed going to 0. But we're going to find out that this series actually diverges. Okay. Another thing to note, by the way, is that this series does have some terms that are negative in it. But I'm still going to compare this using limit comparison. I'm going to compare to this series, just the 1 over n. I know this is the Divergent Harmonic Series. So let's take the limit as n goes to infinity. The terms of my series, I'm interested in finding whether it diverges or not, right here, to this one. Okay. So as n goes to infinity, we already said at the top, the sine of 1 over n goes to 0, right? As n goes to infinity down here, that's going to 0. So this is, again, 0 over 0, indeterminate form. So I can use L'Hopital's rule, right? So that's what I'm going to do in this case. I take the derivative, let's take the derivative of the bottom, that's pretty easy. What's the derivative of 1 divided by n? Derivative with respect to n of 1 over n, right? That's the derivative with respect to n of n to the negative 1 power. I just do it that way, and that is what? Negative n to the negative 2. And so there's my derivative by the power rule. What's the derivative of the top? Well, I've got chain rule there, right? Sine of 1 over n. So the outer function is sine, inner function is 1 over n. Derivative of sine is what? Cosine. Evaluate at the inner function. Times the derivative of what's inside, 1 over n. Well, we just found that. That's times negative 1 over n squared. And what do you note? For n, going to infinity, n is a positive number. These two factors, right, that ratio will be equal to 1, so we can cancel those factors out. And so what am I left with? The limit as n goes to infinity of cosine 1 over n. And I can push this, right, again, inside, the limit inside the cosine function, because it is continuous on its domain. And as n goes to infinity, 1 over n goes to 0. This is cosine of 0, but cosine of 0 is 1, right, which is greater than 0. So again, what do we have? By limit comparison, we have the limit of the ratio of two sets of terms, right? The terms of this series and the terms of this series, and that limit is equal to what? A positive real number. If that limit is a positive real number, the limit comparison test says both series converge or both series diverge. Since I know this series diverges, therefore this series has to diverge by limit comparison. Okay, so there's lots of other examples you can try with using these, and so I'll encourage you to work through the homework problems in the textbook as well as the ones that I have in my homework, non-textbook homework. Practice those, and they're not that difficult in terms of, you do have to show the support for the particular test. As we build more and more of these tests, don't worry about memorizing all the details of those. I'm going to give you a sort of a summary of all the tests, and you'll have that for taking any tests and quizzes and things. But definitely practice working through these, and it's a different sort of thing than what we've been doing for sure. Okay, but in the next lectures we'll continue looking at some other types of tests. In the next lecture we're going to throw in terms that all the terms are not all positive. We have some negative terms that we're adding up, and that adds a little bit of a interesting wrinkle to things. So we'll take a look at that in the next lecture.